Consider two concentric conducting spherical shells as shown in the figure. The inner shell has a radius A and carries a charge plus Q. The outer shell has a radius of B and carries a charge minus Q. The empty space between them is half filled by hemispherical shell of dielectric having permittivity epsilon 1. The remaining space between the shells is filled with air having permittivity epsilon naught. The electric field at a radial distance r from the center and between the shells is. So in this question they have given a shell with a charge plus Q. The shell is at a radius of A. Okay, then they have another shell outside that and that gets a charge of minus Q. Now in this shell has a radius of A. Now in between these two shells what they have filled is half of it is filled with the air that is having permittivity of epsilon naught and another half is filled with the dielectric material having a permittivity of epsilon 1. They have asked us to find what is the electric field in between region between the shell 1 and shell 2. Okay, we will see how to find it. So we know according to Gauss law we can draw a Gaussian surface in between the two shells that encloses the charge plus Q. You consider this dotted line as a Gaussian surface. Gaussian surface. Yes, we know according to Gauss law, closed integral of electric field into dA is equal to Q divided by epsilon naught. If you bring epsilon naught this side, epsilon naught closed integral of E vector dot area, that is equal to Q. Right? We have to find the left hand side and also the right hand side. Okay, for left hand side we will be getting first half is being filled with air. So whose permittivity is epsilon naught. It will be as such. E is a constant in this region because at a distance of same distance you take this distance as r from the center. So electric field is also a constant. So simply you will be getting inside the closed integral area. That corresponds to the left side half, that is air filled region. This is for air. Okay, then plus another side we have a dielectric material whose dielectric constant is epsilon 1. Electric field is also constant and the closed integral of area. This area is for the dielectric. That is equal to what is the charge enclosed by the Gaussian surface? That is the plus Q charge. Right? Now it will be epsilon naught E into what is the area occupied by the air? It will be half of the area of the sphere 4 pi r square divided by 2 because half of the area only occupied by air. Remaining area is occupied by the dielectric constant. Epsilon 1 E into, so here also 4 pi r square divided by 2, that is equal to capital Q. By simplifying it we will be getting and taking all the common terms outside, it will be epsilon naught E. Epsilon naught is not a constant. Here common term. By taking the common terms outside we will be getting E into 2 pi r square epsilon naught plus epsilon 1, that is equal to Q. Here in the question they have asked us to find electric field. So E vector is equal to 1 by 2 pi r square Q divided by epsilon naught plus epsilon 1 into unit vector r cap. So the correct answer is option A. The donor concentration in a sample of N-type silicon is increased by a factor of 100. Assuming the sample to be non-degenerate, the shift in Fermi level at 300 Kelvin is. So in the question they have taken initially the donor concentration, we will take it as Nd, and its corresponding Fermi energy is Ef. Okay, now what they have done in the question is they have increased the concentration. Okay, let it be Nd prime, that is 100 times Nd. Okay, and the Fermi energy level shifts to Ef prime, and they have asked us to find what is the Ef prime minus Ef at 300 Kelvin. Okay, so for initial condition we will write this one. EC, we know EC minus EF is equal to KBT ln of NC by ND. Right, we know this tells us what is the position of Fermi energy level, and for this condition we will be getting EC minus EF prime is equal to KBT into ln of NC divided by ND prime. We will substitute the value of ND prime, we will get KBT ln of NC divided by 100 times of ND. Right, then EC minus EF prime is equal to KBT ln of NC divided by ND minus KBT ln of 100. Right, now we can substitute for this term EC minus EF, so it will be EC minus EF minus of KBT ln of 100. Now we can remove this EC and this side EC, then we will be getting EF prime minus EF is equal to KB into T ln of 100. In the question they have given the value of KBT at 300 Kelvin, 25 milli electron volt into ln of 100. So by simplifying it we will be getting 115.15 milli electron volt. As shown in the figure, an electromagnetic wave with intensity II is incident at the interface of two media having refractive index n1 is equal to 1 and n2 is equal to √3. The wave is reflected with the intensity I of R and transmitted with the intensity I of T. Permeability of each medium is same. Reflection coefficient R is equal to I of R divided by I of I, and transmission coefficient T is equal to IT divided by II. Choose the correct option. So in this question they have taken a two medium having a refractive index n1 is equal to 1 and n2 is equal to √3. Okay, electromagnetic wave incident at the interface, and a part of the beam is reflected and another part is being transmitted. They have asked us to find which among the four options is the correct one. Okay, so first we will calculate the Brewster's angle. According to Brewster's law, tan of angle of incidence is equal to n2 divided by n1. In the question n2 is √3 and n1 is 1. So theta I is equal to tan inverse of √3, that is nothing but 60. So theta I, angle of incidence, is equal to 60 degree. So there is a Brewster's angle. So in the question option A is incorrect because here it is given as a incidence angle as a theta as 0. Okay, now we have to check whether the other three options. So we know that when light falls at a Brewster's angle, the reflection coefficient R is equal to 0. So by using this we cannot eliminate any of this answer, because theta I is equal to 60 degree is given in option C and R is also equal to 0. We know that when polarization of incident light is parallel to the plane of incidence, then R is equal to 0 and T is equal to 1. So when the polarization is parallel to the plane of incidence, T is equal to 1. So this option is a correct one. And if the polarization of incident light is perpendicular to the plane of polarization, plane of incidence, then R is not equal to 1 and R is not equal to 0 and T is not equal to 1. Now based upon this option, so here both has a perpendicular to the plane of incidence, right? So R is not equal to 0. So this option is incorrect. And T is also not equal to 1. So this option is also incorrect. Only answer is option B. Consider a cross-section of an electromagnet having an air gap of 5 cm as shown in the figure. It consists of a magnetic material mu is equal to 20,000 mu naught and is driven by a coil having Ni is equal to 10 raised to 4 ampere, where N is the number of turns and I is the current in ampere. Ignoring the fringe field, the magnitude of magnetic field in air gap between the magnetic poles. So in the question they have given an electromagnet, okay, and it has an air gap. This is the air gap of 5 cm and also it has been filled with the magnetic material having a mu value of 20,000 mu naught, and it has been connected to a coil that has a current into number of turns is given by 10 raised to 4 ampere. They asked us to find what is the magnetic field in this air gap. Okay, so first we will find what is the magnetic field due to this current carrying coil that is connected with the electromagnet. That is given by B is equal to mu naught N into I. Here it has been inside the electromagnet has been filled with the material having the value of mu, so it will be mu Ni. So mu value is 2 into 10 raised to 4 mu naught and N is number of turns per unit length. So N divided by L into I. In the question they have given the value of Ni value, so it will be 2 into 10 raised to 4 mu naught into 10 raised to 4 divided by length of the coil. It is equal to the length of the air gap. So that will be 5 into 10 raised to minus 2 meter. So when we simplify it, we will be getting 2 by 5 into 10 raised to 10 into mu naught. Okay, now this is on medium and here air gap is another medium. So we have to use the boundary condition. So according to boundary condition, B parallel divided by B1 parallel by mu1 is equal to B2 parallel component divided by mu2. We take this as a medium 1 and this as a medium air gap as medium 2, and this B will become B1. We have to substitute the value. B1 is 2 divided by 5 into 10 raised to 10 mu naught into mu2 value is simply mu naught divided by mu1 is 2 into 10 raised to 4 mu naught. So by simplifying this, we will be getting 0.25 Tesla. So the magnetic field in the air gap is 0.25 Tesla. A material is placed in a magnetic field intensity H. As the result, the bound current density is induced and magnetization of the material is M. The magnetic flux density is B. Choose the correct option valid at the surface of the material. So in the question, they have asked us to find which among these four options is the correct one. So we know according to Gauss law of magnetism, del dot B is equal to 0. So if we see the option B is a correct one. Okay. Then we know for a static magnetic field we have current density JB is equal to del cross H. Then del dot JB will be del dot del cross H. We have already studied divergence of a curl is 0. Of curl is equal to 0. So this right hand side will be equal to 0. That is del dot current density is equal to 0. So option D is a correct one. We know that V is equal to mu naught H plus M. Del dot B will be is equal to mu naught del dot H plus del dot M. We know del dot B is equal to 0. That is equal to mu naught del dot H plus del dot M. Therefore, we will be getting del dot H is equal to minus of del dot M. Therefore, we can say option A and option C are incorrect. Answer is option B and option D. An electromagnetic wave having electric field E is equal to 8 cos kz minus omega t y cap volt per centimeter is incident at 90 degree on a square slab from vacuum with refractive index N0 is equal to 1 as shown in the figure. The slab is composed of two different material with refractive index N1 and N2. Assume that the permeability of each medium is the same. After passing through the slab for the first time, the electric field amplitude is volt per centimeter of the electromagnetic wave, which emerges from the slab 2 in the region 2 is close to. In this question, they have taken a square slab that is divided into two equal halves. Okay, and that division makes an angle of 45 degree. One side of the medium is filled with the refractive index of 2.2 and another side have a refractive index of 1.1. Now in this phase, electromagnetic wave incident on the side of 1 and then it goes inside the medium and comes out through the phase 2. Okay, the incident beam has an amplitude of E naught, and now in the question they have asked us to find what is the value of the electric field amplitude that is coming out of the phase 2. Okay, in the question they have given E value as 8 cos kz minus omega t into y cap. So here the value of E naught is 8. So first we will calculate what is the intensity of the incident beam. I naught is equal to 1 by 2 C epsilon naught E naught square. So we will substitute it here 1 by 2 C epsilon naught 8 the whole square. So by simplifying it we will be getting E naught is equal to 32 epsilon naught C. Okay, this is the intensity of the incident beam here. So at this interface 1, at the phase 1, we will calculate at interface 1, we will calculate what is the transmission coefficient T1 and the intensity I1. How much amount of light is been coming out of this phase 1, and that's why it is enters inside the slab. So T1 is calculated by 4 into N1 N2 divided by N1 plus N2 the whole square. Here N1 is equal to 1 and N2 is equal to 2.2. By substituting it, we will be getting 8.8 divided by 3.2 into 3.2. We will keep it as such. Then we will calculate what is the intensity of the beam that is entering inside the glass slab. So I1 is equal to I0 into T1. So I0 is 32 epsilon naught C 8.8 divided by 3.2 into 3.2. So by simplifying it, we will be getting 88 divided by 3.2 into epsilon naught C. So this is the intensity of the electromagnetic wave that is entering inside the slab through the phase 1. Now we will go inside. What happens at this interface we will see. So after entering inside it, the incident angle at this phase is theta I is equal to 45 degree. Now we need to know whether the light is reflected or entirely it is transmitted through the beam. So for that, first we will calculate what is the critical angle. Critical angle theta C is sine inverse of N2 divided by N1. Sine inverse of N2 is 1.1 and N1 is 2.2. So this is sine inverse of 1 by 2, that is nothing but 30. So here incident angle is 45 and the critical angle is 30. Since the incident angle is greater than the critical angle, total internal reflection takes place here, right, at this phase. So entire beam will be reflected at this interface and goes and falls on the another phase, that is at the interface 2. We consider I2 is the intensity of the beam that is reflected from this interface after going total internal reflection. So we can say as the entire beam is reflected, I2 is equal to I1, right? So we can directly calculate what happens at the interface 2, how much intensity of light that is coming out of the phase 2. So now we have to calculate at the interface 2, I3 and T3. So T3 is equal to 4 into N1 N2 divided by N1 plus N2 the whole square, that is 4 into 1 into 2.2 divided by 1 plus 2.2 the whole square. So by simplifying it, you will be getting 88 divided by 3.2 into 332. Now I3 will be I2 into T3. Since I2 is equal to I1, we can write I1 into T3. So I1 value is 88 divided by 3.2 epsilon naught C into 88 divided by 32 into 3.2. We will keep it as such. So in the question, they have asked us to calculate what is the amplitude of the electric field at the interface 2. So we know I3 formula will be 1 by 2 epsilon naught C into E3 the whole square. We know the value of I3, substituted 88 into 88 divided by 3.2 into 3.2 into 32 into epsilon naught C, that is equal to 1 by 2 epsilon naught C E3 square. So C epsilon naught will get cancels off. So you will be getting 88 into 88 divided by 3.2 into 3.2 into 32 into 2, that is equal to E3 square. So by taking root on both the sides, we will be getting, this will get cancels off, so we will be getting 16. So E3 will be equal to 88 divided by 3.2 into 4. We can cancel this. This will be 11 divided by 0.4. So it will be 11 divided by 1.6. So the amplitude of electric field that is coming out of the phase 2 is 11 by 1.6. In the description box, you can find the solution for GATE 2018, 19 and 20 question paper. Please share and subscribe the channel.